Now let's try using these multiplication algorithms with numbers that are not base 10 to see if we really understand how they work. The first thing we need to do is create a multiplication table in base 5. I'm going to do this very similar to how we set up the addition table in base 5. I'm going to represent each of the digits in base 5 using tallies. I'm going to leave 0 off of this table only because 0 times anything is 0, so that gets kind of boring. If I'm multiplying 1 times any group of tally marks, I'm not actually repeating anything here. So 1 times this first group of tally marks doesn't change anything, it's just one tally mark. Same with 1 times 2 tally marks. I'm not creating more images here, I'm just copying it over. And that's because 1 is the identity for multiplication. So we know that 1 times anything does not actually change the value of the product. And I've copied that in my first row and my first column because we know that multiplication is commutative, therefore 2 times 4 is the same thing as 4 times 2. Now let's look at 2 times each of our digits. 2 times each of these groups of tally marks means I need to duplicate each picture. So instead of 1 tally mark, I would have 2. Instead of 2 tally marks, I would have 2 groups of 2. 3 tally marks would turn into 2 groups of 3 tally marks, and then 4 would turn into twice as many there. And now we can count these in terms of base 5. So 2 tally marks is still 2. 2 groups of 2 tally marks, that becomes 4. 2 groups of 3 tally marks, well, that's enough to make a group of 5 with 1 extra left over. In base 5, that looks like 1 group of 5, 1 single, or 1, 1, base 5. 2 groups of 4 tally marks, that's enough to make a group of 5 with 3 units left over. That looks like 1 group of 5 with 3 singles. So we'll fill this into our table. 2 times 1, we already have that as 2. 2 times 2, we'll put in 4. 2 times 3, that looks like 1, 1, base 5. 2 times 4, that looks like 1, 3, base 5. And we can copy that in the column as well. Next, we'll look at 3 times each of these. If I were doing 3, I would triple each one of these tally mark pictures. So instead of just having 2 of each, I would have 3 of each. And then we'll rewrite these in base 5. Oops. So 3 times 1 is still 3. 3 times 2 turns into 1 group of 5 with 1 single. 3 times 3 turns into 1 group of 5 with 4 singles. And 3 times 4 turns into 2 groups of 5 with 2 singles. And we fill those in our table. The last one we need to do is 4 times 4. We really have all of the rest of the table filled in, but for completeness, I'll go ahead and work through 4 times each of the digits just for thoroughness. That's like making 4 copies of each of these groups in parentheses. 4 times 1 is still 4. 4 times 2, that's enough to make a group of 5 and 3 singles. That looks like 1, 3, base 5. 4 times 3, that's enough to make 2 groups of 5 with 2 singles. That looks like 2, 2, base 5. And then 4 times 4, that's enough to make 3 groups of 5 with 1 single. Notice that when I filled out this table, I didn't go through and think about each product as numbers in base 10 and then convert them to base 5. So I didn't say in my mind 4 times 4 is 16 and 16 converted to base 5. No, that's not what we're doing here. We're just looking at regrouping in a base 5 system. So I drew the tally marks out and then I looked at how I could arrange them into groups of 5. And then from there I wrote the number out in base 5. Now that we have our table complete, we can try to multiply numbers. For example, 2, 1 base 5 times 3 base 5. We can try and use the standard algorithm here. That would be 3 times 1, which is 3. And then we would do 3 times 2. And if we come back to our table, 3 times 2 gives us 1, 1 base 5. So this would look like 1, 1, 3 base 5. Let's try using the expanded algorithm with partial products. The 3 times 1 would still be written as a 3, but then 3 times 2, that's actually 3 times 2 groups of 5. So then that would look like, sorry, we wouldn't write it as 2 groups of 5, we would write that as groups of 5 like this. 3 times 2 is still 1, 1, but when we multiply it to the number 1, 0 in base 5, that becomes 1, 1, 0. So we do get the same thing there. Let's make this a little more challenging by multiplying maybe by 2, 3 instead of just 2, 1. Double-digit numbers. So we'll do it in the standard algorithm way. 3 times 1 is 3. 3 times 2 is 1, 1. Put a placeholder so that we can work in our groups of 5 place value. 2 times 1 is 2, and 2 times 2 is 4. Adding up here, I have 3 plus 0 is 3, 1 plus 2 is 3, 4 plus 1 is 1 group of 5. So we write 1, 0. If we do our expanded, we're doing 3 times 1, and then 3 times 2 groups, or sorry, 2 of the groups of 5. So that would look like 1, 1, 0. Then we do 2 in the groups of 5 place value. That looks like 2 groups of 5 times 1. And then we do 2 groups of 5 times another 2 groups of 5. And then we add them all together. 3 plus zeros is 3. 1 plus 2 is another 3. 4 plus 1, that's another group of 5. So we get the same answer here, even if we do the expanded algorithm. Let's do the same problem using the lattice multiplication. All right, 2, 1, 2, 3, and then I'll draw my lattice. What's great about the lattice algorithm is I can do this in any order I want. It doesn't have to be left to right. So I can do 2 times 3 first if I want to, which is one group of 5, one single. I can do 1 times 2 next, which is 0 groups of 5, 2 singles. I can do 1 times 3 after that. And I can do 2 times 2 after that. Notice I did this all in whatever order I pleased. And then we can add down the diagonal. And we get 1, 0, 3, 3 as our answer, again in base 5.